All right, let's just dive right in. Welcome to today's explainer. If you work with embedded systems or IoT devices, you already know that turning a device on isn't just flipping a switch, right? It's actually igniting this incredibly complex, highly choreographed sequence of events. Today, we're going to explore the fascinating journey of the embedded Linux startup sequence. We're tracing the exact path from cold, inert hardware all the way up to a fully functional operating system. Think of this journey as a massive 3D architectural stack. Down at the very bottom, we're starting at the literal silicon hardware base. From there, a single ignition pulse triggers a climb up through some very distinct layers. We go through the bootloader stage, up into Linux kernel initialization, process spawning, and finally, we hit user space, where you get that familiar login prompt. It's a literal ascent, from raw silicon to running software.
So I like to think of this whole process as a highly orchestrated relay race. And here's our track for today. First, the embedded dilemma. Second, phase 1, the bootloader. Third, phase 2, kernel initialization. Fourth, mounting root file systems. And finally, number 5, phase 3, user space.
All right, let's kick things off with part 1, the embedded dilemma.
Before we actually start the race, we kind of need to understand the track conditions, right? We need to know why bringing up an embedded Linux system requires such a specialized multi-stage sequence in the first place. We'll just compare a typical host environment to a target IoT device. Host machines? They have massive storage, tons of RAM, and native compilation capabilities. But our target devices are highly resource-constrained. We're talking low RAM, tiny flash storage. They literally lack the power to host their own native compilation tools. And because we can't build target software on the target itself, we have to rely on cross-compilation. And that necessitates this carefully staged boot sequence to bring the compiled system to life from absolute scratch.
Which brings us to part 2, phase 1, the bootloader.
The starting gun fires, and the very first leg of our relay race begins. This is where the hardware finally wakes up. So what exactly is a bootloader? Well, it's a completely independent piece of software with one singular, dedicated purpose in life. Its whole job is to initialize the raw processor and board controllers, fetch the Linux kernel, and then gracefully pass the baton by transferring control over to it. Basically, it preps the track.
Now, the bootloader has to clear 4 sequential hurdles before its job is done. First up, hardware initialization. Second, downloading the kernel image from flash, or maybe a network. Third, decompressing that image and placing it into a very specific physical memory address, one that's determined by the kernel's ELF header. And finally, number 4, making the literal jump to the kernel.
Let's zoom in on that very first hurdle for a second, hardware initialization. The bootloader configures the CPU speed, sets up memory registers, turns on the caches, and readies the serial port so we can actually see diagnostic messages. It also performs a power-on self-test or post. And hey, fun fact, if you ever want to shave vital seconds off a device's startup time in the field, this post-diagnostic can sometimes just be skipped during warm boots. Pretty neat trick if you're optimizing.
Okay, so before the bootloader leaves the track, it sets up crucial arguments, things like memory size and root device location. It puts these in a designated physical RAM area that the kernel is specifically programmed to read. Then, it executes a jump instruction directly to the kernel's entry point. Boom, the baton is passed. And honestly, this is incredible. Once this jump happens, the bootloader's job is completely finished. That means the Linux kernel can actually reclaim the bootloader's memory space for itself.
Moving right along to part 3, phase 2, kernel initialization.
So the baton is now firmly in the hands of the Linux kernel, and the core intelligence of the system is about to come online. But wait, it doesn't immediately start running C code. Nope, it actually begins at an assembly-level routine, something like head.s. This vital little stub activates the memory management unit, which maps virtual addresses to physical ones. It initializes page tables and zeroes out the BSS space just to prep the environment. Only once this environment is perfectly stable does the assembly routine invoke the massive C function called start_kernel. You can kind of think of start kernel as this highly efficient assembly line. It acts as a central hub that rapidly brings all the major subsystems online. It fires up trap init for exception handlers, init IRQ for interrupts, time init to establish the periodic system heartbeat, and console init so the kernel can start outputting those familiar diagnostic messages you see scrolling down your screen.
And right here is where things get truly fascinating. At the very end of start kernel, the system does something remarkable. The kernel forks. The original thread, which is PID 0, becomes the idle task. It essentially just steps back. Meanwhile, a brand new kernel thread, PID 1, is birthed into existence. This new init thread grabs the baton to handle the rest of the setup, running driver initializations and getting everything ready for the next major phase.
Which takes us to part 4, mounting root file systems.
All right, so PID 1 is running. But to make the system actually usable for human beings, we have to build a vital bridge from the kernel's world into the user's world. The root file system is that foundational directory structure. Absolutely everything else is mounted on top of it. The kernel literally cannot transition to user space without it. If it can't locate or mount this root device, the entire execution halts and it triggers a fatal panic error, unable to mount root FS on device. The bridge is out and the race is totally over.
To build that bridge, embedded developers actually have a few architectural choices. You might use an initial RAM disk or init (RD), which simulates a block device directly in memory. That's perfect for early development or system recovery. Now for active debugging, you might mount over a network using NFS so you can make real-time host modifications. But for the final production release of an IoT device, you're almost always going to rely on a persistent standalone flash-based file system.
Now, the crucial point right before we cross over into user space is resource management. And the kernel has a brilliant trick up its sleeve here. Developers will tag one-time setup functions, like driver registrations, with the init directive. The linker then groups all this use and throw code together. Just before transferring control to user space, the kernel completely frees this contiguous chunk of memory, reclaiming those valuable pages for the system memory manager. Because as we know, in an embedded device, absolutely every single byte counts.
And that brings us to our final leg, part 5, phase 3, user space.
We are finally on the last leg of our relay race, where the complex underlying code finally gives way to a usable operating environment. Remember that PID1 kernel thread we talked about earlier? Well, it executes the execcv system call. And this is incredible. It doesn't just create a new process, it literally overlays its own kernel thread memory space with the sbin/init user space executable. It essentially sheds its kernel skin to become the very first true user space program.
Now, running as a user space binary, sbin/init acts as the grand orchestrator for the whole shebang. It reads the etc/init tab configuration file to figure out exactly what it needs to do next. It runs scripts to mount special file systems like proc, initializes the device's networking, and, most visibly to us, it starts sequentially bringing up system daemons. This includes responding critical processes, like that user login prompt, if they ever happen to terminate.
The exact target state that sbin/init aims for is dictated by run levels. For instance, run level 0 halts the system, and 6 reboots it. But for your normal operations, it targets level 3 for full multi-user command line access, or level 5 if your embedded system includes a graphical user interface. This basically dictates exactly how the environment is going to function for the user.
So, looking back at this complete journey, it's pretty clear that the embedded Linux boot is definitely not just some monolithic block of code turning on. It really is a highly orchestrated relay race. The bootloader primes the hardware and places the kernel. Then the kernel builds the abstraction layers and drivers. And finally, the root file system allows user space to take over and hand you that final prompt. Every single phase establishes the exact initial conditions required for the next runner to succeed.
All right, we've covered the complete track today, from raw silicon all the way to the prompt. Now I want to leave you with a thought-provoking challenge. If you were tasked with shaving vital seconds off the startup time of a highly constrained IoT device, knowing this intricate relay race inside and out, which specific phase or handoff would you tweak first? Would you look at the post tests, maybe the init TRD, or perhaps that init memory reclamation? Think about it. Thanks for joining me on this explainer, and happy optimizing.